Okay, I see everybody starting to come back from the break, and we had two really fabulous talks before the break, and we've got two more on tap here. So our first talk will be by Mike Ramsey-Musolf to talk about fundamental symmetries in neutrinos, the theory experiment interplay. Go ahead, Michael.
Good morning, everybody from Shanghai, China, and good evening to you in various parts of the US or Europe or wherever Asia you may be. Let me start by thanking Krishna for the invitation to give this talk, and to all of you for joining in and supporting the DNP in our community during this very challenging time. So as advertised, I'm going to be talking about some developments in theory related to fundamental symmetries in neutrinos and the interplay with experiment. And I just want to start by mentioning that there are hosts of collaborators whose work undergirds what I'm going to be talking about in the next little while. And I've highlighted in light blue the many PhD students who've contributed to this work, as well as a number of postdocs and more senior collaborators. And in particular, I want to highlight at the bottom of this slide the what I call my cohort of colleagues who are part of the topical collaboration in nuclear theory, focusing on fundamental symmetries, in particular neutrinoless double beta decay. And also thank other collaborators who didn't make that list, but who I've worked with over the years and continue to rely on, as well as give an apology to anyone whose work I'm not able to cover during this talk because of the finite time period. So let me just start by the main messages that I hope you'll take away from this discussion. And the first overarching point is to remind ourselves that our fundamental symmetry tests in neutrino studies in nuclear physics continue to address compelling questions about the fundamental laws of nature. And these questions motivate the search for physics beyond the standard model. The second is, as you know, there are significant advances in experimental sensitivities, and these advances are challenging nuclear theory to push both the state-of-the-art and standard model computations, as well as to delineate the broader implications of this part of our program. And third, which is what I'll really highlight, are some recent theoretical developments that I think are meeting this challenge head-on, uncovering some new puzzles and pointing toward what I call the next horizon in experimental sensitivity. So the outline is, I'll start with a broader beyond the standard model context, then focus largely on the question of whether or not there's new lepton number violation in nature beyond the quantum lepton number violation of the standard model, and in particular how that may play out in the interplay between neutrinos double beta decay, cosmology, and collider physics. In the last part of the talk, I'll discuss some developments in precision tests and a very brief outlook at the end. So let's start with the BSM context. And the way I like to think about this is the questions that we are trying to answer. I put them in two categories, what I call the must answer questions and the should answer questions. The must answer questions are facts about the universe that we need to explain, which we can't in the standard model. And those include, in the upper part here, the composition of the energy density of the universe, in particular for nuclear physics, the baryonic symmetry is a particularly important question. And the second would be to try to explain these puzzles about the origins of the neutrino mass and neutrino properties. On the other hand, there are the should answer questions, which are more sort of conceptual theoretical, and these have to do with what controls the quantum corrections to scalar fields in nature, in particular the Higgs field, and also the vacuum energy associated with the cosmological constant. And we really are in, conundrum about these should answer questions. And many theories beyond the standard model continue to try to address them, but they all have to address the questions, it seems to me, on the left column here. So undergirding our quest to address these questions is the other question, which is, what is the mass scale? And what are the coupling strengths associated with the new physics that would address these questions? So here's a very simple representation of the landscape. On the horizontal axis is the coupling. On the vertical axis is the mass scale, anchored to the weak scale, MW. Many theories live at sort of order 1 couplings and very high scales. there are equally compelling ideas at very light mass scales and very small couplings. And somehow we hope that the interplay between theory and experiment will teach us something about where in this plane the answers to those fundamental questions live. In nuclear physics, the way I like to divide our program in searching for these answers is into four sort of components. There are searches for new CP violation with electric dipole moments that bear on the origin of matter. There are the searches for new lepton number violation, which also bear on the origin of matter. That's the neutrinoless double beta decay. Then there are precision tests that I divide into studies of electron and muon properties. And then there are the tests of weak decays. And both of these really can bear on the question of the mass scale of new physics. So in this talk, I'm going to focus largely on neutrinoless double beta decay, but spend a little bit, maybe the last third, on the precision tests. And we'll see how far I actually can get on those. So let's start with lepton number violation, the quest to find and see neutrinoless double beta decay. And I want to talk about the interplay with cosmology and colliders. And so let's step back a little bit and remind ourselves why this is such an important part of our program. We made a big push for it in the current long range plan, which is now almost 6 years in the making. And it's good to remind ourselves why this is such an important program to continue to address. And I think there are two reasons. The first is the big one, which is that it addresses some of the most compelling and fundamental open scientific questions that we have. And the second is that over the years, since we first were discussing it, I think our awareness of the broader implications of neutrinoless double beta decay is even deeper than ever before. And so I continue to remain very enthusiastic about this part of our program. So let's talk about the fundamental questions. The fundamental question is, what's the mass term that we write down for the neutrino? Is it a Dirac mass like all the other elementary fermions in the Standard Model? Or is it a Majorana mass, which is shown in the Lagrangian on the right? And that is a lepton number violating mass term. It is dimension 5 in our jargon in theory. And that means that it is associated with a new mass scale that comes into the denominator, lambda. And what we don't know is, what is this mass scale? If neutrinos are Majorana particles, what is lambda? So back to our plane of mass scale versus coupling, we really have this open question about where lepton number violating dynamics live. Where is lambda in this plane? Historically, people have thought, based on the seesaw mechanism, that it's at very high scales, but it could be at much lower scales. And so we really need some insight from experiment as well as theory to tell us. The way I like to think about this is to divide the possibilities into three broad sort of regimes. The very high scale possibilities, which live far above the weak scale. The second is sort of more closer to the weak scale. And a third is the possibility that the scale is very light. So when this gets applied to neutrinos double beta decay, a process which, as you know, nuclei change total charge, but not, the charge is conserved, of course, but 2 electrons come out. The underlying dynamics, we don't really know. All we know is the outcomes 2 electrons and no neutrinos. And so one can divide the possible mass scales into 3 broad categories for underlying dynamics. The first, the very high scale, there are only 3 light neutrinos in nature, and the scale is the very high seesaw scale. The second is that there are 3 light Majorana neutrinos, but there are additionally lepton number violating interactions at the TeV scale or weak scale. And the third possibility is that there are more than 3 light Majorana neutrinos. So I'm going to briefly review the first one, which is what we're probably most familiar with. And here is the set of sensitivity plots that I think our community is now very well aware of, which shows on the vertical axis an effective light neutrino Majorana mass relevant to double beta decay. That's on the vertical axis. And on the horizontal axis is the lightest neutrino mass. The left panel is the sensitivity for the inverted hierarchy. The right panel is for the normal hierarchy. And the goal sensitivity for the next generation experiments is to reach down to the bottom of the inverted hierarchy. So this has been our poster child, what I call the standard mechanism, or poster child mechanism. And let's keep in mind that underlying it is this picture of the seesaw mechanism, which says, in addition to the light neutrinos in nature, there is some very heavy right Majorana neutrino. And so this is what undergirds the idea that neutrinos might be responsible for the matter-antimatter asymmetry. So let's remind ourselves how that works. So there are four components to this so-called leptogenesis scenario. The heavy neutrinos decay out of equilibrium in the early universe. If they're Majorana, they can decay to particles and antiparticles. The third is that the rates for the two possibilities can be slightly different due to the presence of CP violation in the heavy neutrino sector and the resulting excess of leptons over antileptons in this decay asymmetry can be converted into a baryon asymmetry by the standard model of sphalerons. For us, of course, it's the second bullet that is key, having Majorana nature of neutrinos. The light neutrinos implies that the heavy neutrinos in this setup are also Majorana. So how does this possible picture change if, in addition to the three light neutrinos and the associated heavy right-handed neutrino, there are lepton number violating interactions at the TeV scale? So I'm going to try to address that possibility now in the rest of this part of the talk and really talk about the implications for leptogenesis. I will also talk about the connection with what we learned from cosmology on the sum of the light neutrino masses and connection with collider physics. And I'll say a little bit about some progress as well as some open questions about how we reliably compute the TeV scale contributions. So let's start with the implications for leptogenesis. Here's a way to think about it, which is organizing the energy scales relevant in the early universe from the very low scales at the bottom of this vertical axis to very high scales at the top. The standard thermoleptogenesis scenario that I just outlined really lives at the very high scale, sort of from 10 to the 9 GeV and above. And now what we want to ask is, let's suppose there are additional lepton number violating interactions that live at the TeV scale or below. Well, it was realized a couple of years ago by several people that the presence of these additional lepton number violating interactions would be quite dangerous for the standard thermoleptogenesis scenario for reasons that I will outline in a minute. And what I'm going to illustrate is some of our work that shows how this works in concrete terms and link this with some of the experimental sensitivities. So now I need to do just a little bit of math, so I'll keep equations, I hope, to a minimum, but for leptogenesis, there are really two important equations that we have to address. One is the evolution of the abundance of the heavy neutrinos. That's the first equation. Z is a dimensionless inverse temperature. And the second is the abundance of baryon minus lepton number violation. If we look at the first term, we can see that this depends on two quantities, what's called a decay term and a scattering term, D and S. And the rate for this abundance goes like the difference between the neutrino abundance and its equilibrium density. And with the CP violation, those heavy neutrinos are decaying, and so that leads to being a source for the B minus L abundance, which is in the second equation here. And in addition, in that equation, there is a term that likes to wipe out the B minus L abundance, which is what's relevant for the leptogenesis process. And this comes from inverse decays and other processes. So there's kind of a wrestling match between decays and washout that ultimately determine whether or not leptogenesis works. So washout processes are in general dangerous. With the heavy neutrinos, there are processes where a lepton can be converted into an antilepton through the exchange of a virtual heavy neutrino. This is a lepton number changing process that's CP conserving. And so because it converts lepton to antileptons, if we have any source of an asymmetry, this tends to wash it out. But for the heavy neutrino only case, this still seems to work. What's dangerous is if there are new interactions at lower scales, TeV scale, those can in principle really wipe out the lepton asymmetry. So if you would observe TeV scale lepton number violation, this could be quite fatal for this very beautiful idea for generating the matter-antimatter asymmetry. So I'm going to illustrate this in a very simple model that involves two new particles, a scalar particle S and a new Majorana fermion F. For aficionados who are listening, here's the interaction Lagrangian. It comes with two couplings, and I won't spend time on the details here. But the presence of these interactions can lead to a new set of washout processes that change lepton number by 1 or 2 units. I've just illustrated in this set of diagrams here some of the possible contributions to the washout term. But what I want to do is show you the impact. So what's shown here is at the bottom of your slide are two different cases. On the left plot, there is on the vertical axis the abundance of the heavy neutrinos in the blue and the baryon minus lepton number asymmetry in the orange. And this is for a case where the new particles are at the TeV scales, but the couplings are pretty small, 10 to the minus 3. And what's important is to note that the orange curve at the far right, and I should have said the horizontal axis is inverse temperature. So as time is increasing, we're going further and further to the right. The orange curve sort of flattens out and remains constant to today. And therefore, we have a source of the baryon asymmetry through the Sphaleron processes. But on the right, look what happens when you turn up these new interaction couplings by just a little bit to 10 to the minus 2. Then the orange curve dies away. And so we have no source of a lepton asymmetry in today's universe, and therefore no baryon asymmetry. So one can translate this into an exclusion plot in this simple model just to illustrate. The two couplings in the theory are shown here. In the pink region, the B minus L asymmetry is washed out, so we have no baryon asymmetry generated through leptogenesis. And in the white region, B minus L survives. So if we're in the pink region, then there would have to be some other alternative baryogenesis mechanism at work that would live at the TeV scale and below, and that would already be very interesting. So I now want to talk about how experiment might bear on this possibility. And I'm going to talk about implications for collider searches in nuclear physics. And I want to start with a kind of a simple cartoon of the Feynman diagrams that show up in the two different regimes. On the left is at the quark lepton level what neutrinoless double beta decay looks like. 2 d quarks goes to 2 u quarks, and out come 2 electrons. On the right, I've taken the same ingredients and turned it into a proton-proton collision diagram where I just turn around some of the arrows. So I pull a d quark out of a proton and an anti-u quark out of the other proton. And the same interaction then leads to outgoing high energy quarks or jets and 2 electrons. So in a collider experiment, somehow didn't, yeah, there we go. In collider experiment, the signature is a pair of same sign leptons and 2 jets, 2 high energy jets. So we now want to compare the sensitivity of that process with neutrinoless double beta decay, where in the upper diagram on the lower part of the screen, I can integrate out the heavy particles and just treat it as a contact interaction and try to analyze the relative sensitivities. So I now need to make an interlude for how we do this. We do this using effective field theory. And the starting point is to write down the interactions, those contact interactions at the low energy scale. That's shown in this orange box at the top here. There's a set of operators at the quark level, and that they multiply lepton number violating bilinears at the lepton level. I've just shown you one 4 quark operator here that is part of the possible list. And the name of our game really is to take this underlying quark lepton Lagrangian and map it onto a low energy Lagrangian, chiral Lagrangian involving pions and nucleons, which is something with Gary Prizeau and Peter Vogel we worked out, in 2003. So what this allows us to do is then take these interactions that are lepton number violating at the quark lepton level and turn it into hadronic lepton number violating interactions that then can contribute to the neutrinoless double beta decay process as shown in these diagrams here. And so this is, of course, helpful because we can now do real many-body nuclear calculations with the corresponding operators. And in principle, it allows us to be systematic about organizing the size of the contributions. So the way we did this in 2003 was with so-called Weinberg counting, and you can organize the relative size of these different contributions in terms of the small momenta in the problem times some coefficient that depends on the underlying operator in the purple box. So for example, for one of those operators, k pi pi has no momentum dependence, and so the whole amplitude with 2 pion exchange is 1 over p squared. Whereas for another operator, it really implies 2 derivatives on the pion, and so the amplitude is actually order p to the 0. So there's a nice sort of way of organizing one's thinking about the relative size of these different contributions. And so the name of the game then is to use chiral symmetry to map these operators onto the effective Lagrangian. There's been a lot of recent work, which I'll just mention, in effective field theory, trying to do this, and also now to calculate the relative operator coefficients at the hadron level, the low energy constants. Some very interesting developments in lattice QCD. So this can now be taken to translate into our, our underlying model into the various contributions to the double beta decay process. For the model that I'm illustrating with here, the leading order contribution is this double pion exchange term here. And the new development is that we have realized that we need to include a short distance counterterm along with this long range effect. And so I want to say a little bit about this because this is a significant development in the field. It was realized a couple of years ago by the authors listed at the top of the page here that even for the light neutrino exchange case, which is shown in the diagram on the far left, there are strong renormalization effects shown on the far right that imply the need for a short distance counterterm. And for the EFT aficionados who are listening, you can think about it in terms of the bubble diagrams on the lower part of this diagram here. C and C tilde are the strong interactions that go into the EFT. And it turns out those are divergent diagrams, and so one has to include a counterterm called G nu on the lower right. There's a similar problem for the TeV lepton number violating case, where if we take the 2 pion exchange and embed it in this these bubble diagrams, there's a similar UV divergence that also implies the presence of a contact operator, and that has to be counted as order p to the -2, even though naively in the Weinberg counting it is order p to the 0. So determining the low energy constant is a big challenge for this field, and there is some interesting developments in lattice QCD trying to do that, and some other efforts using isospin symmetry or chiral symmetry, but we're still in the sort of puzzling situation of how big is this counterterm. So what we can do is use naive dimensional analysis to try to estimate the size while people work on strategies for doing a real first principles calculation. So I'm going to now take this and translate it into our back to our connection with leptogenesis. And that's what's shown in these plots here. Let's look at the lower left, just as an example. Again, to remind you, in the pink region, leptogenesis would be non-viable. And now the green corresponds to the sensitivities of neutrinoless double beta decay, both the present limits from Kam-Lan-Zinn and the ton scale sensitivity shown in the lighter region with the long dashed line. And you can see that if there were an observation of neutrinoless double beta decay and it were associated with this TeV scale lepton number violating scenario, that would be totally fatal for standard thermal leptogenesis because we would live in the pink region. The blue is the high luminosity LHC sensitivity under different scenarios for the mass spectrum of the new particles. In the left, the mass spectrum is very degenerate, and so neutrinoless double beta decay would win over the high Lumi LHC. But over on the far right, you can see that for a different mass hierarchy, the LHC could actually extend far into the further into the leptogenesis fatal region. And so depending on where one is, one gets observations from one or both energy regimes. That would tell us something very interesting about the source of the lepton number violation, and again, would have interesting implications for the matter-antimatter asymmetry. So I want to say a little bit now about the connection, another cosmological connection between double beta decay and neutrino masses, in particular the sum of the light neutrino masses. And as you may remember, cosmology is getting more and more sensitive to the sum of the light neutrino masses, and this has important implications for our thought of how sensitive neutrinos double beta decay would be. And just to remind you here, the idea is the matter power spectrum is very sensitive to the sum of the neutrino masses. I won't go through the details of why, but the increasing information from cosmological observations is putting tighter and tighter constraints on the sum of the light neutrino masses. And that can be translated into our poster child scenario for neutrinos double beta decay. So again, on the horizontal axis are different ways of organizing the neutrino masses. Let's focus on the middle panel, where one has the sum of the total sum of all the light neutrino masses, and the vertical axis is the effective neutrinos double beta decay mass. The current cosmological bounds, excuse me, are right around where the orange line live. The neutrinos double beta decay ton scale sensitivities are given by this red line here. The curve that stops, the band that stops, is the inverted hierarchy. And so you can see that it doesn't go arbitrarily down in the sum of the light neutrino masses. And in particular, there's some chance that the next generation of cosmological observations will put the sensitivity all the way where the green dashed line is. And if it shows that for a certain mass range, there is no observation of the light neutrino masses, then the inverted hierarchy would be ruled out, and one may be in a very tiny region of parameter space for an observation of a neutrinos double beta decay experiment. So this has kind of been a little bit of a nightmare scenario for people in the field. So I want to show you that if you add new TeV scale lepton number violation to the theory, this picture can change quite dramatically. And we'll do this in the context of a time-honored BSM model, the left-right symmetric model. I just want to flash for you here. There are a number of Feynman diagrams that can contribute to the double beta decay process now that involve the exchanges of the new heavy particles in the left-right symmetric model, the right-handed gauge boson and a doubly charged scalar, for example. I want to focus on the diagram on the right, where one has an exchange of a right and a left-handed standard model like W boson. This is called the left-right contribution. And if this contribution is included, there is a long-range enhancement to the neutrinos double beta decay amplitude associated with these pion exchange effects. And that's what we really analyzed in this recent work. And again, just to highlight which of these diagrams at the hadronic level this is relevant to, it's the one on the far left. So here are the results. What's shown here is our sort of standard way of plotting things. On the horizontal axis is the sum of the lightest neutrino mass. Not the sum. And the vertical axis is now the effective double beta decay mass. The dark green dots correspond to analyzing the left-right symmetric model in the absence of that left-right diagram that I showed you previously. On the other hand, the light dots correspond to the effect of including the left-right contribution, which leads to this long-range enhancement. The expected sensitivity of the ton scale experiments is given by the expected limit down at the bottom, and you can see that in the inverted hierarchy case, we're still safe, but in the normal hierarchy case, if that's what the cosmology experiments told us, then there may or may not be sensitivity of neutrinos double beta decay. But on the other hand, including the long-range chiral enhanced left-right contribution, all these light dots then emerge, and those are well within the sensitivity of the next generation experiments. So it's interesting to translate this into the plot involving the sum of the light neutrino masses, which is shown again on the horizontal axis here. The vertical axis is the effective mass. Now we see the red and the light dots corresponding to the short range only, and now the long range contributions. The current cosmological bound is shown in gray here. If we look at the ultimate cosmological sensitivity, you can see that even if cosmology gets us down to the bottom of the range, there's still ample room for an observed effect in neutrinos double beta decay due to these long range chirally enhanced effects in the presence of the left-right, so-called left-right mixing scenario. So it's not a nightmare scenario. It just means that the observation of double beta decay would teach us something very interesting about the mass scale associated with the lepton number violation. In particular, it could really be this TeV kind of scenario. So let me now turn a little bit to precision tests. I'm not going to be able to finish everything here that I wanted to. I realize I've been a little overly ambitious, so I'll start and we'll just maybe save the rest for questions. So I want to start with weak decays, beta decay in particular. As you know, very time-honored and important question that nuclear beta decay addresses is CKM unitarity, the first row. And the sum of the squares of all the elements is supposed to add up to 1. So we define the difference between 1 and the experimental results as delta CKM. Here are the inputs into that test as of a couple of years ago. I won't go through the details, but the bottom line is there was very good agreement with CKM unitarity at the about 5 times 10 to the minus 4 level. Really, at 2 sigma, it would be 10 to the minus 3. Now, the hope is that one can push the sensitivity of this test an order of magnitude. And the reason, so the goal would be 10 to the minus 4. And the reason why that's interesting is that if there's new heavy BSM physics that comes into the process, and if it's a tree level sort of effect, then the mass scale that's being probed is sort of 10 TeV. And that's interesting for the high energy community because 10 TeV is the mass scale associated with solutions to what's called the little hierarchy problem, which I won't have time to say anything about, but it's a very interesting mass scale. So that's our goal. So the problem is not right now experiment, the problem is theory in getting there. As you probably know, to extract, in particular, VUD from nuclear beta decay, one has to apply a number of corrections to the observed so-called FT values. And I've taken here John Hardy's, one of John Hardy's plots of the different sizes of corrections for different ways of extracting VUD. The important one right now is on the far left, which is the super allowed nuclear decays, where you can see in the bottom part of this plot, the yellow, the experimental uncertainty is much smaller than the red, which is a radiative correction uncertainty. And then there's a blue, which has been the conventional understanding of the uncertainty associated with many-body nuclear physics. So the recent developments is that there's been a factor of 2 reduction in the red. And on the other hand, there's sort of a no-win theorem seems to be going on here. What we've realized is that the error bar for the nuclear correction is probably underestimated. And so it's larger and it increases due to previously emitted contributions. So let me just tell you a little bit about where this problem lies. It lies in a diagram, a loop diagram called the W gamma box, shown on the left. The amplitude for this W gamma box is given in the right. And there are 2 contributions here. There's a short distance contribution that involves a logarithm that is resulting from the sampling of momentum scales all the way from the weak scale down to the hadronic scale lambda. And then there are long distance contributions that go into a kind of a constant I'll call C gamma W. And the problem for us is not the short distance. The problem is calculating reliably the long distance, okay? Because that's really sensitive to the hadronic and nuclear dynamics. So again, a little reminder of terminology, because I'm going to define several corrections. There's kind of a zoo of corrections that go into beta decay, and I don't expect you to remember all of these now, but to get the so-called corrected FT value, you have to apply what's called an outer radiative correction. There's a nuclear structure correction that involves the nuclear energy independent part of that box graph. There is a nuclear wave function correction. And more recently, it was realized there is an energy-dependent part of that box graph that has to be included. So once one gets the corrected FT value, you can then extract VUD either from the nuclear decays, or you can do the same thing for neutron decay, knowing the decay asymmetry in the lifetime that's shown on the right. In both cases, there is a radiative correction that still has to be analyzed. That is the hadronic physics sensitive part. That's delta R superscript V. And that is something where there's been progress. And the progress comes through using what's known as a dispersion relation to calculate this radiative correction. I don't expect you to follow this formula, but the radiative correction can be written in terms of integrals over two of structure function called F3, and that integral in turn can be related to something called M3, which is a Nachmann moment. So for people doing electron scattering, the Nachmann moment is a very interesting object. And why this is interesting is that we can use data, or at least theory that tries to match data, to compute these inputs for the radiative correction and do a better job on computing this box graph than we did in the past. And so that's really what we did. To do that, one has to analyze the data we have on the nuclear responses and leptoproduction. The leptoproduction response for the single nucleon is shown on the right. That's the green box. And for the free neutron, I'll just tell you the punchline is that there's been a significant increase in the size of the radiative correction and a decrease in the error bar. And if one takes this at face value, this would imply actually a significant deviation from CKM unitary. Now, in the last minute or so, before I stop, I want to mention that this is not the end of the story, because we are analyzing, the best measurements come from nuclei, and so one has to analyze the same inputs, the response function for nuclei, where the high energy part of the response function that appears on the nucleon still goes into the nucleus, but the elastic contribution becomes part of what's known as the quasi-elastic response. And here is where there's been a new development also, where the quasi-elastic response was really not treated correctly in the past. And that's the other part of our work that I want to mention. The shift in that contribution is given in the lower part of your diagram here. There's the change with respect to what's called the Born contribution that Ian Towner and John Hardy have been computing over the years, compared to the full quasi-elastic contribution, is of order 5 times 10 to the minus 4, which is as big as the quoted error, and we give a pretty generous error bar on that. So if our goal is to get the uncertainty down to 1 times 10 to the minus 4, there's really an open challenge for nuclear structure here to do a better job on this quasi-elastic contribution, as well as, I think, the low-lying part of the nuclear response function. And that I'll just mention is work in progress. So the part that I apologize in particular to electron scattering people is new developments in the computation for parity violating Moller scattering. I'm going to just jump to my conclusions, and we could in principle come back to this if people want in the question period. But let me just reiterate what I opened this talk with, is that this field is really exciting because of the big questions that are being addressed. The experimental sensitivity advances have pushed us in nuclear theory, and I hope I've highlighted for you some interesting developments that are, I think, meeting this challenge, but uncovering some new puzzles that require further work, and hopefully pointing us toward the next horizon in experimental sensitivity. So I will stop there, and thank you all very much.
Thank you, Michael, for a fabulous talk. People can either enter questions in the chat, or you can raise your hand. We have one question already in the chat from Ken Hicks. What are the limits on inverted or regular hierarchy of neutrino masses from neutrino oscillation experiments like T2K and MINOS? And should that result also factor into theoretical models?
Thank you, Ken, for the question. I don't have the limits right now. There are, I just didn't bring those with me into this talk. Yes, there are increasing indications for the normal hierarchy. How that, of course it factors into people's models. But, what I was really trying to emphasize, Ken, is that this, again, goes into the 3 light neutrinos only paradigm. And I think we need to stop thinking of that as the primary possibility, because there is that whole landscape for where lepton number violation could be living. And so if there are TeV scale lepton number violating interactions, the neutrino oscillation implications would tell us about the light neutrino part of the double beta decay input, but not the TeV scale lepton number violating part. And so for those scenarios, the results from T2K and MINOS are a little less relevant because these interactions are not really relevant for neutrino oscillations.
Thank you, Michael. Are there other questions? You can either raise your hand or put them in the chat. Okay, we have a question from Alejandro. Let me allow you to talk. Go ahead and ask your question.
Hello, can you hear me?
Yes.
Yep.
Oh, yeah. Hello, Michael. My question was about slide 51. I was wondering whether the relative areas of the different points that you show there is relevant, and if so, you know, how many are on each? It's hard to tell here. You say if they, even if they lower the limit down to 0.06 or something like that, that's still a very large section. But just looking here, it looks very narrow, but maybe there are a lot of points there, and it's just hard to tell.
Yeah. So, you know, density of points in scans is certainly one way to think about things. You know, the point is that compare the dark with the light red. Yeah. So the dark is very narrow. That's the sort of approaching the standard, the 3 light neutrinos only scenario, where there's a very narrow sliver of possible observation. But the, you know, the density of points, you know, you would want to really redo the scan, you know, with the cosmological bounds as a prior. And so I don't think that one should overinterpret, you know, white areas there. The point is, you can live above 0.01 in a way that you couldn't without the long range contributions. And yeah, so you know, nature's going to, if this model's right, nature's going to pick one point. You know?
Right.
So a scan with a flat prior is one way to try to assess probabilities, but I don't know. Nature picks one point. Yeah.
KK, do you want to ask your question?
Sure, Michael, thanks for a great talk. So the LHC's dilepton limits, do they just continue to get better if, you know, when you talk to LHC colleagues as they go morph to high luminosity, or, you know, 10 years from now, do they wipe out ton scale double beta decay? Do you have a sense for that?
Well, so first of all, let me go, thank you for the question. Let me go back to this plot here. And let's remind ourselves what these colors are. So the light and the blue are the LHC sensitivities. Let me just do And so the light purple is the high Lumi LHC. So that's the ultimate. And the interplay with double beta decay really depends on, you know, the model parameters. It's very sensitive to the spectrum of the masses. So in the left panel, you can see that even the high Lumi LHC would not compete with the ton scale experiments. On the other hand, for a different mass hierarchy in the model, high Lumi LHC would extend beyond the ton scale experiments. So, you know, I don't think there's a one size fits all answer on this question. And I think what's more important is that imagine taking the input from both. Let's suppose both ton scale and LHC see a signal, then you would probably be somewhere in this model on the panel on the right. And in both cases, you would then conclude it's TeV scale lepton number violation and likely to be fatal for leptogenesis.
Thank you.
So, go ahead.
I was going to say, I think we have time for one more question, and I'm going to allow Linder to talk and ask his question.
Hi, Michael. That was a really nice talk, and I had a question about the same plot. So, how sensitive is sort of this exclusion plot, or sort of the pink band, on your model dependencies. Like, let's say that we see Neutrinos double beta decay and some sign of TeV lepton number violation. Does this necessarily rule out sort of this high scale leptogenesis? Or how general is this argument?
Well, it's pretty general, up to one caveat. And let me just say, what we are doing now is kind of marching through classes of simplified models to see what this looks like in different scenarios. And part of that, you know, affects the ton scale sensitivities because of this chiral symmetry mapping onto the effective field theory. The sensitivities, excuse me, the green will shift around a little bit. But the generic sort of sensitivity interplay is pretty robust, I think, up to this caveat. And the caveat has to do with flavor. It could be that, you know, this is all first generation leptons and quarks, but it doesn't tell us what's going on in second and third generation. And so an open question is, if we include the effects of flavor in leptogenesis, you know, are there other low energy observables that could teach us about the corresponding constraints on lepton number violation in second and third generations? And there are a combination of collider physics and charged lepton flavor violation experiments would be very, very interesting. And so that's part of our longer term sort of program here, is to unpack that in more detail. So it's a great question, and I would say work in progress.
Thank you very much, Michael. I'm sure we've got more questions. Vincenzo has put a link in the chat, which I will share with everybody, but I think we need to move on to our next talk. And our last speaker for the night is Professor Sharona Gordon, who will talk about, wait, can you share your screen, Sharona?
Okay.
And she will talk about Physics 2, harnessing individual and community power to prevent sexual harassment. So we are very excited to have this talk, Sharona.
Well, thanks. And thanks so much, Sherry, and also to KK for inviting me, and to all of you for visiting with me for this hour. What I want to talk to you about today is sexual harassment, not as the blame and shame game, but as something that all of us can be effective in addressing. And the metaphor that I'll be telling you about in a bit is that sexual harassment is like an iceberg, where you only see the worst of the worst, and most of what happens is hidden. But before we really get into the details of that, I want to ask a question that many people have been asking, which is, why does a discussion of sexual harassment belong in a scientific meeting? And why does this discussion even belong in science? And if you have that question, you wouldn't be the only one. In fact, it's come up quite a lot recently. And what I'm showing on the screen is a quote from Science magazine from a famous scientist, Bob Weinberg at MIT. And this was in the context of the recent National Academy of Sciences, Engineering, and Medicine vote of its members to ask whether, if a member had been found through their institutional due process to be responsible for sexual harassment, they should be ejected from the academy. And Bob Weinberg said, before there's a mad rush to approve such an ejection procedure, it might be useful to ask whether sexual harassment by a member has anything whatsoever to do with their credibility as a scientist and the soundness of their research accomplishments, the criteria that were used to elect them in the first place. And so many people do wonder whether this discussion of sexual harassment is an appropriate one to have in science. And so all of us, I think, can think of many, many cases that we've heard about in the news or through the grapevine, in which someone did something very unethical, and as a consequence, their science wasn't any good. But let's take an even more extreme example. Let's take an example of scientists whose work is unquestionably good, but whose behavior is in modern terms seen as sexual harassment. And that is Watson and Crick, the scientists who first published the structure of DNA. So Watson is a very well-known misogynist and racist, and Crick is known as the nicer of the two. But both of them had things to say about women. For example, in his book, The Double Helix, James Watson said, clearly Rosie, and here he's referring to Rosalind Franklin, whose X-ray data he used, had to go or be put in her place. The thought could not be avoided that the best home for a feminist was in another person's lab. But even the nicer of the two, Francis Crick, was not progressive. He said, I'm afraid we used to always adopt, let's say, a patronizing attitude towards her, referring to Rosalind Franklin. And Nancy Hopkins, an MIT biologist who's done a lot of work for gender equity in sciences, was a graduate student with Watson. And she said, when I was an undergraduate at Harvard, I was sitting at my lab desk one day, writing up notes when the door of the lab flew open. There stood a scientist I didn't know but recognized instantly. Before I could rise and shake hands, he had zoomed across the room, stood behind me, put his hands on my breast and said, "What are you working on?" It was Francis Crick, the co-discoverer of the structure of DNA. Now, I don't know anyone who says that DNA doesn't have a double helical structure, that questions the methods that Watson and Crick used to solve the structure. It's a finding that has clear integrity. And so you might ask, well, is their sexually harassing behavior really a challenge to that work? I mean, if we kicked Watson and Crick out of science because of sexual harassment, we wouldn't have the double helical structure of DNA. And I have a couple of answers to that. One is, none of us is irreplaceable. If Watson and Crick hadn't published their structure of DNA in the year that they did, someone else would have within short order. But the second thing I would say is that, yes, they contributed a lot to science, but we will never know the loss to science of the contributions from people who they drove out. And so we have this leaky pipeline of women and people with other marginalized identities leaving science in droves. In my field, women have received more than half the PhDs and been more than half of the postdocs for over 30 years, yet our representation among the ranks of faculty is barely budged. So what about the loss from all those people who have been driven out of science by sexual harassment? And so I say that, in fact, people's behavior does affect the integrity of the scientific enterprise, and that the integrity of the scientific enterprise is far more important than any one person's work. So now I'd like to tell you about my favorite metaphor, and this comes from a 2018 report from the National Academies on Sexual Harassment. So it tells us that sexual harassment can be divided into three types: sexual coercion, which is when favorable professional or educational treatment is conditioned on sexual activity; unwanted sexual attention, which is unwelcome verbal or physical sexual advances, which can include assault. And those two types are above the waterline. They're like an iceberg. 10% of the mass of an iceberg is above the waterline. And that's the 10% of incidents of sexual harassment that everyone would recognize as sexual harassment. But there's a third kind called gender harassment: verbal and nonverbal behaviors that convey hostility, objectification, exclusion, or second-class status about members of one gender. And gender harassment constitutes 90% of the incidents of sexual harassment. And if you think of the above the waterline forms as the come-ons, the below the waterline forms can be thought of as put-downs. They're bullying, right? They're absolutely bullying. And like any other kind of bullying, they're damaging, but it's particularly important to recognize gender harassment for what it is, because all of the research shows us that people who experience gender harassment and don't know to label it as such experience far more negative physical and mental health consequences than those who recognize it for what it is. And in fact, when pervasive and prevalent, gender harassment can be just as damaging as sexual coercion and unwanted sexual attention. The other thing I want to say is I get a lot of questions when I give these talks about, well, do you want to regulate all of our relationships? You know, I'm a biophysicist, so I recognize that I spend more than half my awake hours in the lab. Of course, we don't want to regulate relationships, but sexual harassment is not about relationships. It's about power. Typically, in fact, the common behaviors aren't even about attraction. They're motivated by a desire to devalue women or punish those who violate gender norms. And so this distinction is really very important because we only recognize that top 10% as a form of sexual harassment, but the 90% that's below the waterline is still doing a tremendous amount of damage. So when I first started out in academia, I didn't even really know the term sexual harassment. You might remember the movie 9 to 5 with Dolly Parton, and she was being chased around the desk by Dabney Coleman. That only came out in the early 1980s. So what we know, though, is that sexual harassment isn't just something that happens in the workplace if you're in business or in finance. In fact, compared to every public sector, private sector, and government workplace, academic workplaces have the second highest rate of sexual harassment ahead of every other institution except for the military. Think about that. We have a higher prevalence of sexual harassment than any public sector, private sector, or government sector, except for the military. And what this pie chart shows, I'll draw your attention to the light blue 37%. Those are the women who don't experience sexual harassment. All the other pieces of the pie are women who experience one or more forms of sexual harassment. So this similarity to the military, that we're second only to the military in incidents of sexual harassment, is instructive because we can ask, what is it that we in the academic sciences have in common with the military that makes sexual harassment so prevalent? The number one thing is our hierarchical power structures. Those of us with tenure especially have tremendous power over our students. We write letters, we fund them, and so that hierarchical power is really problematic for making a difference in power that prevents people from insisting on their safety. Another thing is the isolation of many academic scientists within research labs or field sites. It's pretty common for postdocs in my field to not even know the names of other postdocs on the same hall because they have their noses to the grindstone in working so hard to be successful. Another issue is the perceived tolerance of sexual harassment in academic sciences, which has been quantitatively measured, and policies focused on protecting institutions from legal liability. And the following one is a quote directly from the National Academy's report, uninformed, unfocused, and uncommitted academic leaders. And then finally, low representation of women in academic sciences, particularly in leadership positions. So in all these ways, we really have a lot in common with the military, and that can be useful in helping us come up with solutions. What the research tells us is that sexual harassment doesn't just happen. That in fact, it's based on having incivility in the environment. The National Academy report says that incivility is low intensity deviant behavior with ambiguous intent to harm the target in violation of workplace norms for mutual respect. So one area that I take issue with in the report is this phrase that I've underlined. What I would say is that if nearly 2/3 of women are experiencing sexual harassment in the environment, then it is not in violation of the workplace norm. In fact, it is the workplace norm. So what research tells us is that sexual harassment most often takes place within workplaces that are enriched in disrespectful behavior. And importantly, when workplaces take measures to improve the level of respect in their environments, they see decreases in incidents of sexual harassment. So Unfortunately, incivility is like secondhand smoke, that when you have one person who is uncivil, who behaves in a disrespectful way, they act as a role model to others. But the flip side of that is also true, which is that people who demonstrate respectful professional behaviors also act as the social contagion to inhibit sexually harassing behaviors in people who would otherwise exhibit them. And so I see the National Academy's report, even though it's full of pretty horrifying statistics and very upsetting examples, to actually be incredibly empowering and optimistic, because what it tells us is that we don't have to change the entire environment in one fell swoop, but that even when one person at a time makes changes in their behavior, it has the potential to influence the behavior of others. So sexual harassment is like an iceberg, and we should think about that metaphor and how it's instructive for what we can do about it. And so I'd say, well, why is the ice frozen? And the answer is that the ice is frozen because the water is freezing. And so if we were to take an ice pick and pick away at each little outcropping of ice, so long as the water remains freezing, so long as there's that freezing equilibrium, new ice would form. And so if we want to address the root causes of sexual harassment, the root cause of ice, then what we need to do is to warm the temperature of the water. And so that's really what I want to spend the next few minutes talking about, is what does it mean to warm the temperature of the water? So if the ice represents the incidence of sexual harassment, what does the water represent? I would say that the water is our environment, and more specifically, the water is our community. Well, what then sets the temperature of the water? I would say that what sets the temperature of the water are the interactions that each and every one of us have with each other each and every day. Now, pre-COVID times, that was more meaningful because we actually ran into lots of people during the day. But it's still the case that we do interact with people, and that every interaction is an opportunity to influence the temperature of the water, to either make our environment more welcoming, to warm that water, or to reinforce the old ways of looking at things in which people were expected to leave parts of their identities at the lab door. There's a word for it. There's a word for it when you're not welcome in the entirety of who you are. It's called code switching. Code switching is when you have to hide part of your identity to fit in to an environment. And there's lots and lots of evidence that demonstrates that code switching hurts people. So if we are to really warm our water, if we are really to strengthen community, what that means is to really make sure that each and every individual within our environment feels welcome for the entirety of who they are. When I was first an assistant professor, at that time I had only 2 kids, and now I've got 4, but then I had 2, and people told me, don't put up pictures of your children in your office, because if you do, then when people come to meet with you, they'll see that you're a mother, and they'll say, oh, well, she's not really committed to her career in science. Now, that was 25 years ago, and to some extent, things have changed. I haven't heard of anyone being told not to put up pictures of their kids in their office, but it's still the case that we do have a construct of a professional persona in which someone leaves part of their identity at home. And that is something that absolutely needs to change for people to feel more welcome in our scientific environment. But I want to talk about another thing that I like about this metaphor. I've been an activist working to reduce sexual harassment in the academic sciences for several decades. And for most of those decades, when I would talk to men about sexual harassment, they would tell me that they felt blamed. And it was only through thinking about this iceberg metaphor that I realized that men were feeling blamed because I was blaming them. And of course, when people feel blamed, they are not thinking of themselves as part of the solution. And if we are really going to change our environment to be more welcoming, all of us need to be part of the solution. And what that takes is recognizing that all of us have been socialized in this same environment in which the stereotype of a scientist was a white man. And that's not because we're bad people or good people, it's just because of how we grew up. And because of that socialization, all of us have these instinctive thoughts about people who are different and people who are different in the workplace, and that when an incident of sexual harassment occurs, and really now I'm talking about the below the waterline, put down forms of sexual harassment, that those incidents are really just natural consequences of being in this frozen water. The way that ice is a natural consequence of the freezing temperature, these below the waterline forms of incidents of sexual harassment are natural consequences of our traditionally male-dominated academic environment. And when you think about it that way, then blame is not a useful construct. Instead, we need to shift our focus away from blame and instead think about our shared responsibility moving forward and how it's going to take all of us working together to really warm the waters and change our environment. So the report from the National Academies makes 15 recommendations, and it's a 300+ page report. It's available freely on the National Academy's website, and I recommend reading it. But I only want to talk to you about the last of these 15 recommendations, which is to make the entire academic community responsible for reducing and preventing sexual harassment. It says that all members of our nation's college campuses, students, trainees, faculty, staff, and administrators, as well as members of the research and training sites, should assume responsibility for promoting civil and respectful education, training, and work environments, and stepping up and confronting those whose behaviors and actions create sexually harassing environments. It really couldn't be more simple. Every one of us needs to step up and examine our own behaviors and look for ways in which we can bring more civility and respect into the workplace. So I know that sounds simple, and boy, I wish I could give you a list of behaviors that are welcoming and behaviors that are unwelcoming. And most of the training that's out there actually focuses on lists of what I call stop behaviors. Don't put your hands where they're not wanted. Don't talk about women as inferior. Lots and lots and lots of stop behaviors. And what I found is that most people have a really hard time getting enthusiastic about what they're not doing. Nobody comes and pats you on the back and gives you a cookie for not pinching someone on the behind. On the other hand, it's much easier to become excited about go behaviors. A go behavior is something like asking someone in the hallway, "How are you? How was your weekend?" A go behavior can be as simple as when you're leaving work in the middle of the day to pick up your kids, if you're the PI, say that you're leaving to pick up your kids. Model being a fully realized human being with outside interests and hobbies and family. A go behavior is asking a student who seems to be struggling if there's anything they can do to help. A go behavior might look like putting up pictures of your kids in your office. Go behaviors are self-reinforcing because they feel good and they're immediately effective and promote learning. So I said that what we need to do is warm the water, and that the water represents our community, and that the temperature of the water is set by the individual interactions that we all have with each other. And so there are concrete go behaviors that we can practice that really help to eliminate sexual harassment as well as other forms of bullying. Model respectful professional behavior. So saying that we don't want people to have to code switch to come in and be scientists is not a license to behave unprofessionally. We still expect professional behavior, and we can model what it looks like to be a professional who's also a human being. It means valuing individuals. Sometimes that means making your classroom with people sitting in a circle instead of standing at the front lecturing. Sometimes it sounds like giving criticism in a kinder way. Welcome all aspects of people's identities. We also need to help people to recognize healthy versus toxic environments. And that goes to one of the risk factors for sexual harassment, which is these isolated workplaces. The more opportunities we create for what has been pejoratively called networking, but could also be termed community building, the better a position people are in to recognize when they're in a toxic environment, and the more connections they'll have with others to do something about it. Building community is also about sharing best practices. Now, what you do in your workplace might not suit what I do, but I may still be able to learn from it. And it also gives us the opportunity, the more people we know, to stand in solidarity with them when something happens. A lot of times, as an individual, each of us might not have the power to change someone's situation, but we can at least make sure that they don't have to go through it alone. So I founded an organization, Below the Waterline, to build community and drive positive culture change. And I didn't do this in my role as, a scientist who has positionality in my university. I did this just as a person who feels responsible for and accountable to my community. I put up a shingle and said, who wants to talk about sexual harassment? And we started having discussions in which we read the literature and shared views. Since then, I've been going around and teaching departments how to be welcoming and more inclusive. I started a peer supporter program and a faculty allies program. I learned something about restorative justice and participate in community restoration circles. These are things that fit with me and what I'm good at. But all of you have skill and all of you have power. And I would encourage you to look at where the intersection is between what you're good at and what your community's needs are. And think about what you can do to contribute. It might mean going to a rally. It might mean bringing in, well, pre-COVID days, bringing in coffee to your students. It might mean having more office hours. Again, it might mean thinking about how you can reach out to trainees who maybe aren't getting the mentoring that they need. So for me, it was organizing and starting programs, but all of us can do something. So really, I'm a teacher, like I think probably most of you are. And if you're anything like me, standing in the front of a classroom, or in this case, in front of a Zoom screen where I can't see any of you and I can't see you raising your hand, that's not nearly as fun as interacting. And I would like to have the opportunity to hear from you how this resonates with you in your workplace, what ideas you might have for how to do things differently, and what you see as the challenges. But I want to leave you with a quote from the National Academy's report. It says, placing responsibility and control for sexual harassment planning and response at the highest administrative level, guided by attorneys, would likely produce a different organizational culture and climate than one guided by faculty, students, and service providers. And really, this is already happening. Because each of us, as a member of the community, as individuals and groups of individuals, are not stepping in, we're allowing our culture and climate to be guided by a litigious, liability-focused force. And that's one that doesn't align with my values, the way solutions that are focused on lifting people up and helping them would be. And so with that, I'd really just like to open it up to your comments and questions.
Thank you, Sharona, for a very nice talk and lots for us to think about. We already have some questions in the chat. Feel free to keep typing them in the chat, or you can raise your hand if you'd like to ask it yourself. The first question from Patrick: is there any evidence as to whether the pandemic and working from home has reduced or increased sexual harassment?
So what we know, thank you for that question. You know, these really are unprecedented times, and I know it's a cliche, but it's true. What we know is that there have been large increases in young adult mental health crises. There certainly were those before as well, but a recent study found that in the last 2 weeks, something like 17% of 18 to 24-year-olds have seriously considered suicide. So how is that related to sexual harassment? What I think it shows is that everyone is under a lot of pressure, and parents with young kids at home are under even more pressure. And so I haven't seen any evidence about whether the incidence of sexual harassment have increased or decreased, but I would speculate that the impact of the sexual harassment that is occurring is more outsized than it used to be, because everyone is really in such a vulnerable state.
Thank you. A question from AJ. Did any of the surveys you mention or cite give any data about harassment of people who are genderqueer? And did any of them mention any distinction between the types of harassment felt by cis and non-cis groups?
Oh, that is a great question. And I should have mentioned that. So the report is great in many ways, but it's not perfect. And some of the ways that it falls short is, one, it focuses on white women. And second is that it focuses on cisgendered straight women. But there are an increasing number of data sets that show that non-gender conforming folks and non-white folks face higher rates of sexual harassment, sometimes much higher rates of sexual harassment. So for trans women and trans men, their rates of sexual harassment are probably at least 35% higher than for people who present as female and were assigned female at birth. So this question of intersectionality is an incredibly important one that I think really deserves a lot more attention.
Great. So there's a comment here from Jason that says, the freezing water feeding the iceberg put the chilly environment discussions I've attended in much more understandable light as to how environments tilt behaviors. Excellent analogy. Thank you. And I have a question from Ali that says, a lot of these solutions seem to sit at the individual level. Can you speak to the institutional level changes that can be implemented, things that individuals can do to pressure institutions to change effectively? Can you speak to the interplay between individual and institutional change?
Yeah, I am not optimistic about top-down change. Universities and other large research institutions are like the Titanic. They're very hard to steer, whereas grassroots movements are more like kayaks. And so I've put most of my efforts into changing things at the grassroots level. But in the last couple years, I've also had a role as an associate dean in my school and have formalized some of the programs I've developed, like the Faculty Allies. And what I found is that you can make localized changes in institutions. The leadership at my school has been incredibly supportive of these programs, but that ultimately it's a lot like how we passed civil rights laws in the 1960s, and yet people of color are still discriminated against. The legal policy changes are absolutely necessary, but they're not sufficient. And I think it takes both top-down and bottom-up approaches. And, you know, like I said, each of us has talents and ways of working that feel right to us. And there's no right way or wrong way. If you feel moved to work at the institutional level, that's awesome. My preference is really to work at the grassroots. I do want to address a question that came in about my choice of using the #MeTooSTEM hashtag in the abstract. I sent in the abstract before I was aware of a lot of that harm, and I would not do it again today.
Thank you. Another comment from Erin, just in case folks ask, what about specifically in physics? And she would like to refer people to the survey done at the APS conference with undergraduate women in physics that 75% of female undergraduate physics majors reported sexual or gender harassment. Yeah, it's not surprising. I wish I could say it was surprising. I think that from the physics faculty that I've interacted with, even though they anecdotally seem to be more heavily male represented than in the biomedical research field, what I found is that the environments actually seem pretty comparable. Right. And there's a comment sort of, and maybe you can comment on it, is official paid maternal and parental leave would be a good start. A lot of female faculty have to cobble together some combination of sick leave, time off, unpaid time to be able to care for their children. Yeah, you know, that is a way in which grassroots efforts can make a big difference. Nancy Hopkins, who I mentioned earlier in my talk, was a pioneer for working for parental leave, and grassroots movements in Washington state, where I'm from, have recently gotten a new state law that entitles all parents to 12 weeks combined leave that can be split between two parents. I also got a question of what's the ultimate resolution for cases like the DNA pioneers. Unlike the arts, where appreciation is largely subjective, we don't have the option to discard important work done by horrible people. I don't feel this has been fully addressed in science. Yeah, so I think that it is changing, and that the incentives are not really any different than in the arts. There's a reason that Harvey Weinstein's horrible behavior was tolerated for so long. It's because he brought in a lot of money. But I do want to shift the focus from those worst case incidents to back down to gender harassment, because the above the waterline forms of sexual harassment, the sexual coercion and unwanted sexual attention, occur at higher rates within environments that have a lot of gender harassment. And so ultimately, the root causes are how we respect individuals and how we value individuals. And the same way that somebody smoking in the middle of a restaurant these days is anathema, my hope is that one day minor gender harassing comments made in a public space will also just not be tolerated. Thank you. Golden had his or her hand up, and I just unmuted you. So go ahead and ask your question.
Hi, I wanted to ask if you have any advice for people participating in international collaborations where some people might use different cultural norms as kind of an excuse for sexual harassment? That's a great question. I had a PhD student in my lab who was from Ukraine, and she didn't agree with my talk the first time she heard it. She said that her old advisor used to comment on her looks every day, and that he just really meant it as a compliment. And when I asked her, okay, but did he do that to the men? No, well, he didn't really do it to the men. And so the point is that he used the time he had to interact with her, not to talk about science, but to talk about how she looked. And
I don't think that we're going to easily change that except by modeling better behavior. So I don't think that there are easy solutions that'll change it in the short term, but I think that there really is hope that in the longer term, we can make a difference. I would say that if there's behavior that's problematic, that asking someone who you trust with more power to intervene might be helpful, but always make sure to do it in a way that feels safe.
Okay, I think we have time for one more question. I don't see anything in the chat right now. I don't know if anybody has one last question.
Sherry, I don't think I can raise my hand. This is KK. So
You can talk.
thank you. So Sharona, thank you so much for the great presentation and all this, how you initiated this wonderful discussion. I was particularly struck by your last slide, where I think if we are not all feeling incentivized to do the go suggestions, go behaviors that you talked about, which I think is a great way, by the way, to incentivize all of us. The fact that lawyers and administrators can take over our environment is a very, can you speak more to that? I think we need to be more scared about that, and we need to be activated by it.
Most, if not all, institutions in the US have Title IX offices, and typically these Title IX offices are meant to be enforcers of negative behavior, of addressing negative behavior and discipline. But in fact, their role is to protect the institution from legal liability. They're not there to solve problems. They're not there to protect trainees. They're not there to protect people with less power. They're there to protect the institution. And if you think of the kind of culture and environment that falls out of an ass covering kind of mentality, I don't know, it's not the kind of culture that I want to live in. What it means is that we only get to address problems when they get to the most escalated levels. When what we want is to reach out to our colleagues who, most of whom have very good intentions, but just have, socialized bad behavioral habits, and ask how can we support our colleagues to do better without having to turn them into the Title IX police, where things are going to be, escalated and out of control.
Right, that makes sense. So the point also, I guess, is that we need to be extra vigilant to make sure we don't get into a situation, and so the go behaviors are an important aspect of trying to reduce the chance of something untoward happening, which will get the police out.
That's right. In no way do I want to discourage people from reporting sexual harassment if that's what they choose. And again, mostly what I talk about and think about are the below the waterline forms of harassment, which certainly do not meet our behavior bar based on our values, but also oftentimes do not meet the bar for being illegal.
Yeah, thank you for that.
Great. Thank you very much. I don't know if anybody else has another question. Otherwise, I would just like to say thank you to Sharona and to Michael, both for fabulous talks and lots to think about in different ways. And to tell everybody you've got a half an hour, and then there's a virtual tour of the NSCL or RIC users group or a Symmetry Magazine information session. So take a break, get yourself something to drink, and then come back and join one of those. We'll start again tomorrow morning at 8:30 in Central Time, and you can translate that to your time zone with another day of very exciting talks. So thank you all and have a good night.